So in this section we're going to look at our translating and stretching and shrinking of the sine curve, similar to what we did back in chapter 4. For example, general example is, suppose we've got either a sine or cosine graph in the form of y minus k equals some constant a times sine of quantity b x minus h. An example that might be y minus 2 equals 3 sine of pi times x minus 1. What do each of these numbers here do? And that's what we're going to explore a bit. And some of them is pretty easy. If I replace y with y minus 2, we know that that simply is going to transform my graph and move it up 2 units. If I replace x with x minus 1, I'm going to simply move my graph right 1 unit. Everything will translate right 1 unit. If I multiply and compare, for example, sine x versus 3 sine x, we remember that's going to be simply a vertical stretch by a factor of 3. Each y coordinate, sine x, will be multiplied by 3. So that's going to be a vertical stretch by a factor of 3. So the replacing y with y minus 2, replacing x with x minus 1, and changing the amplitude, doing a vertical stretch or shrink by this multiplicative factor here, this constant here, that's pretty straightforward. This part in here gets interesting, order of operations and what actually is happening here, what this constant's going to do, we want to take a little closer look at. So let's take a look here at y equals sine 4x. We remember that if we replace x with 4x, we're going to have a horizontal shrink by a factor of 1/4. So we know horizontal shrink factor of 1/4. So if I think about that, my original sine graph has a period of 2 pi. And we remember the sine graph from 0 to 2 pi, we complete a full period. So if we horizontally shrink by a factor of 4, that period of 2 pi gets shrunk by 1/4, and so my new period then turns out to be pi over 2. And if I look at this in general, for the sine graph or the cosine graph, if I look at this constant here, that's going to appear in front of the x in parentheses, I would have in general 2 pi over that constant, we'll call it b, equals my new period. And that's going to be perhaps something that you want to keep track of. Or you can think it through each time. You can say, hey, my period's going to be shrunk or stretched by a certain amount, and I get my new period. That's how I'd kind of prefer you to do it. But if you want to keep track of a formula to memorize, period of a function divided by the horizontal stretch or shrink factor is going to give you your new period. So, in short then, my new period here is going to be pi over 2. So my graph then I know is going to go from 0 and it will complete a full period by pi over 2. There's another way I can look at that here, and that would be the following way. I know that if this, what's in parentheses here is 0, that would be the start of a period. Sine of 0 would be my start of a period. And if I get up to 2 pi, then I will have a whole period completed. So what I could do also is say, hey, I want to have 4x be 0. Where does 4x equal 0? Well, to start with, x equals 0 will make 4x 0. I then want to go up to and get 4x to be 2 pi. How does 4x become 2 pi? If I solve for x, x is pi over 2. That means from 0 to pi over 2 for sine of 4x, actually what I'll be going between is this is sine of 0 to sine of 2 pi, which would be a full period. So doing it this way, I can also see that getting this quantity 4x to be 0, starting at 0, getting this quantity to be 2 pi, starting at x is pi over 2. From 0 to pi over 2, I get a full period. The period of this function is pi over 2. And I know if I start at 0 and go to pi over 2, I can sketch and get the same sketch that I got right here. So let's take a look at this one. Similar. We've replaced x with pi times x. Since pi is greater than 1, we know we have a horizontal shrink by 1 over pi, a factor of 1 over pi. So I know one way to look at it is to take my period, and if I'm going to horizontally shrink it by a factor of 1 over pi, I divide by pi, and I know then my new period is going to be 2. One way to look at it. The other way, again, we said is we could say, what value could I put in to make pi x be 0, the start of the period of sine? And if I want pi x to be 0, I could start with x equals 0. I also want pi x to be 2 pi. That would mean that x then would have to be 2. So I get a full period from 0 to 2, or my period's 2. How would I sketch this graph? Well, I get a full period from 0 to 2, and my amplitude, max, mins don't change at all. How about sine of 1/6 x? Again, we can view it that horizontal shrink or stretch idea. Since 1/6 is less than 1, I know that I'm going to have a horizontal stretch by a factor of 6. So if my original period was 2 pi, and I stretch that by a factor of 6, my new period will be 12 pi. 2 pi times 6, in other words, is 12 pi. Same idea we did before also. If I want to have that 1/6 x started at 0, I would need x is 0. That 1/6 x, make it to be 2 pi. I would then want x to be 12 pi. So from 0 to 12 pi, I get a full period in. That's a horizontal stretch by a factor of 6. So from 0 to 12 pi, I get a full period in. And that would be my graph of y equals sine of 1/6 x. And I simply would make sure I get a full period graph, starting and end point of a full period. So how about if we look at y equals sine of negative x? We remember from our previous work, if we replace x with negative x in a function, we reflect over the y-axis. So if my original function here looks something like this, here's my sine x on this side, 1 period, full period. If I reflect that over the y-axis, I'm going to look something like this. Over the y-axis. And now over here I had here's the other half of my sine function. If I reflect that over the y-axis, I'm going to end up with this over here. And I want to look at that for a minute. And that's what we've considered replacing x with negative x reflect over the y-axis. Take a look at these two graphs. How also do they appear to be related? You might want to hit pause and think about it for a minute. If you're back from your pause, we note that it would appear that one is the opposite of the other. So that would mean then that sine of negative x equals negative of sine x. And that should be familiar to you. If we have, say, x here, and we have a sine value, and we look at negative x down here, it's the opposite of the sine of x. So indeed, sine of negative x is negative sine x, and that's consistent with what we just did with our graphing. So there are at least two ways to look at graphing something like sine of negative x. So let's put this together a bit. I've got sine of 4 times x minus pi over 2. I know that this x minus 2. I know that x minus 2 is going to shift my original sine graph 2 units to the right. I know this 4 is going to change my period. 4 is greater than 1. And I know therefore there's going to be a horizontal shrink by a factor of 1/4. So my new period I know is going to be 2 pi over 4 or pi over 2. And I know I'm going to shift 2 units to the right. Question is order of operations going to matter here? In other words, could I take my sine function right here, shrink its period to horizontally shrink it in on both sides by a factor of 1/4, and then move 2 units right? Or do I move everything 2 units right and then shrink everything in? And that's what we'd like to consider. And I'd like you to take your calculator and confirm which one is the correct order of operations. In other words, do I shrink horizontally and then move 2 units right, or do I move 2 units right, then shrink horizontally? So, grab your calculator, make sure you're in radian mode, and see what you get. And then come back. So you should have discovered that for the order of operations here, what you're going to do first, this 4 times x minus 2, is you're going to do the shrink first, that horizontal shrink first, and then everything will move 2 units to the right. So if I want to graph one period of this, I know to make this 0, I would start at 2. I know my period's pi over 2, so if I move pi over 2 units to the right, to 2 plus pi over 2, one full period, a piece of this graph, would be from 2 to 2 plus pi over 2. So again, I'm going to take my original sine graph, shrink it horizontally by a factor of 1/4, and then take and move everything to the right 2 units. So thinking about this is about negative 1.57. The stuff that I'm moving over here 2 units to the right, it's going to be something that's coming from over here, is going to wind up being my piece here that I'm going to see here at 2. Because if negative 1.57 moves to the right 2 units, this piece is going to move to the right of the y-axis. So the actual period that I've drawn here would have come from sliding one of these over. So the other type of problem in the section, in addition to wanting to be given to sketch a graph of a trig function that's been transformed horizontally or vertically, stretched or shrunk, is if you're given the equation of some graph, you're told it's some sine or cosine wave, and you want to come up with an equation for it. How can you do that? Well, we'll take a look at one here. Let's suppose we have a minimum value. This is again going to be a local minimum at 0, 2, and I know I've got a local maximum at 8, 8, and I want to write a cosine. Let's write a cosine equation for this graph somehow. A couple ways I can see it. I can see that, hey, I've moved, if I were to slide this graph over here and put a maximum here on the y-axis, my basic cosine curve, we remember, looks something like this. From 0 to 2 pi, I get one period. So if I were to think about if I were to slide this given curve over here, slide this point over to here, I would have taken my cosine graph originally and slid it this way. Problem is I'm not sure where that is. I do know I am given these coordinates here for a local max at 8, 8. I also could think about if I had my cosine curve, if this point here were on the y-axis, if I slide it this many units to the right, then I get myself to 8, 8. So it looks like I could take a cosine graph and slide it here 8 units to the right, and that's going to get my max moved over 8 units to the right. I know my amplitude here, if between 2 and 8, if that distance is 6, halfway in between is going to be my midline, if you will, of my sine wave. So I know my amplitude's 3. If my amplitude is 3, from 2 up to 3 units up would take me to 5, so I know everything's been moved up 5 units. So I can start thinking about how to write this cosine equation. I know I'm going to have a y minus 5. Everything's been moved up 5 units. I know my amplitude is 3. And I know I want to write a cosine graph here, I told you. And now all we've got to do is figure out what's going to go in here. And I know my period is going to be, well, if I go from a lower local min here to a local max here, that's going to be half of a full period. And that's 8 units. So it looks like my period here then is going to be 16 units. So if my period is 16 units, I know that 2 pi over that coefficient b is going to give me my period of 16. So if I solve that for b, I then get b is going to be pi over 8. So if I put a pi over 8 in here for my b, and then we've said to get a cosine, it looks like if I were to move this over here 8 units, I would go then replace x with x minus 8. And we can try this out for a bit. Let's see. If we look at our period, 2 pi over pi over 8, that equals 2 pi times 8 over pi, which equals 16. So that my period checks out. I'm coming up 5 units. Amplitude's 3. I know I'm moving right 8 units. Looks good. And then what you can do, if you want, you may check on your calculator and see if indeed you get the points. If you have 0, you're going to be looking at here a 0, 2. Does that appearing on your calculator when you graph this? When you do a trace, are you winding up with 8, 8 on your graph? Do you have a period of, is the point over here, if my period is 16, is the point 16, 2 also on the graph?